Hey guys, so we are going to be talking about 4.4 comparing linear and nonlinear functions today. Apologize for any background noise. I'm recording this during y'all's lunch hour and other classes near me do not have lunch right now, so you might hear a little bit in the background. But today we're going to be talking about what's the definition of nonlinear. Okay, so what are we looking at? And then if we're given a function, okay, we want to make sure that when we look at a table, a graph, or an equation, how can we say yes or no to linear? Is it linear or nonlinear? And what are we really looking for when it comes to that? Okay, so that's what we're going to be working on today. So, nonlinear function. A nonlinear function does not have a constant rate of change. Okay, so the key word here is does not have a constant rate of change. We have quite a few words in here with our math, and I would like to make sure that we're all on the same page about what they mean. So, when we talk about function, remember back in the first half of chapter 4, we were talking about how a function for every input or x value, there is exactly one output, okay, or y. So for functions, remember when we were going over functions and we had those mapping diagrams and we were drawing the arrows and we were talking about how things could only have one arrow coming off of every single input. That's what we're talking about. So when we're answering the question about function, this is the definition we're talking about. Okay, let's see. So if we come back to our definition, again, we're just kind of setting some of the groundwork for what these different words mean. I see the word in here, rate of change. And when we think about rate of change, this is probably one of the most important pieces of the definition because it's saying that for it to be nonlinear, it does not have a constant rate of change, which means if you flipped it on its head, a linear function does have a constant rate of change, okay? And when we say rate of change, well, what is that? What am I looking for? So when I think of rate of change, I'm thinking of a way to move. And when we were talking about y equals mx plus b, we were always looking at our slope and our y-intercept, and our slope is the way to move. So when we think of rate of change, I need us to start thinking about that variable m, about slope, about change in y over change in x. Or maybe you're thinking slope formula, y2 minus y1 over x2 minus x1. Maybe you're thinking of rise over run. All of these things are a way to talk about rate of change, okay? So we're trying to make sure that we can look at all the different things, tables, graphs, equations, and determine what is the rate of change. Because to answer the question about nonlinear or linear, we need to know, does it have a constant rate of change? So this piece is really, really important. All right? So if we keep moving on, let's dive into linear versus nonlinear table. Okay, so even though we were defining functions earlier, we're going to now assume that everything they've given us is already a function. That's already said yes, because remember, function has to do with inputs and outputs, right? Inputs, outputs. But when we're talking linear, we're really thinking in the simplest terms, straight line. Okay, is it a straight line? If I walk along, do I have a constant rate of change? That's what I want to know, okay, of change. These are two different questions, guys. So on this table, we're talking linear versus nonlinear, which is why we're over here. This is what we're focusing on. We're saying, does it look like a straight line? Is it constant rate of change? So when we're looking at tables, here I've got two tables. We'll call this table 1. We'll call this table 2. When you jump the table, is there a constant change in x and y? So this is the question we ask ourselves when we're looking at a function table and say, is it linear or nonlinear? So when we say jump, we are going to look at how it changes. So when I go from 3 to 6, I add 3. When I go from 6 to 9, I also add 3. When I go from 9 to 12, I add 3. Now, when I was in this row of information, I was here on the x, which means, my change in x equals 3. And the reason I can write this is because every single time I went, it equaled the same number, okay? So if I come to the bottom row of my table, now I'm looking at y, and I'm saying, can I write something for change in y? If I go from 40 to 32, I went down 8. When I went from 32 to 24, I went down 8 again. If I go from 24 to 16, I went down 8. So if someone were to say, what was the change in y? Every single time it was consistent, okay? So we're going to be looking at these jumps here to determine if there's a constant rate of change. So constant rate of change, we said slope equals the change in y over the change in x. And really what we're asking with this is, could we fill this in with numbers based on consistent jumping? So the change in y is -8, and the change in x is 3, which means at any point in time when we jump, do you see how this is -8 and 3, -8 and 3, -8 and 3? So because that is constantly what that is, constantly doing the same thing, it's going down 8 and it's going over 3, then I would say, yes, this is a linear function, okay? And any time that you say something's linear, you should be able to tell me what the slope is, all right? Whether it's from a table, a graph, or an equation. Okay, so let's do the jump method again on table 2. So we start here on the x's, and I say to get from 1 to 3, I added 2. To get from 3 to 5, I added 2. To get from 5 to 7, I added 2. Okay, so I would say for my change in x, it is consistent, and it was 2. Now when I come to my y's, I jump from 2 to 11, and to get there, I added 9. To get from 11 to 33, I added 22. To get from 33 to 88, I added 55. So when I say change in y equals, well, it varies. And the word varies is not a number. So when I want to write change in y over change in x equals, it's not possible, right? Because I don't have a number for change in y because it varied all the time, which means that there's not a consistent slope. So I'm going to determine that it is non-linear, okay? So if it's non-linear, then I'm not able to say what the slope is because the slope is a constant rate of change. So whenever you guys are looking at tables, when it talks about showing your work or explaining why, all of this jumping, all of this annotating is helping explain why you got to your answer. So please make sure when you look at a table, you don't just put the answer, you show the jumps so you can show your thought process of how you got to your answer. All right? All right, so we're going to move on from table, and now we're going to talk about an equation, okay? So we're still asking the question, linear versus nonlinear. So again, function, if we talked about the definition, was inputs, outputs, linear, nonlinear, constant rate of change. So for an equation, when you solve for y, meaning you want it to be in the format of y equals, does the equation look like y equals mx plus b? Okay, so we're going to solve first. That's the first step. When we solve and make the equation look like y equals all the other stuff, and we fill it all in, does it look like that? Or can it look like that? Okay, so here's our first example. Here's the first one. Y equals 4x. Okay, so if I try to say what is m and what is b, I could say, well, there could always be an imaginary plus 0, so b is 0. But when I try to say what is m, I'm like, well, this piece right here doesn't look like mx. It looks like m divided by x. Do you see how x is here in the denominator? So when we have fractions, we have the numerator and we have the denominator. So this x right now is here in the denominator. This x right here, if we put all of this over 1, this x is in the numerator. So does this look like y equals mx plus b? No, it doesn't, because this x is down in the denominator. So when I answer the question, I would say nonlinear because x is in the denominator. Ooh, if I can spell it. All right? So whenever we're looking at this y equals mx plus b, and I've kind of written over that one, so I'll write it again here. What we're really looking at is this invisible exponent. Do you see that invisible 1 that we tend to not write? But it's there. And what we're trying to do is see if that exponent matches up here. Okay? And so when we get into exponents in the next chapter, we'll understand why this doesn't match this based on this exponent right here. So just as an aside, if you had y equals x cubed, we would immediately say nonlinear because when we look to the exponent here, the exponent is not 1. If we were to try and make it look like y equals mx plus b, we could always add the plus 0 and we could put the invisible 1 in front, but we also are looking at this exponent to make sure that it's a power of 1. All right? So back to our example here already set out. So example 2, can this function right here be called linear or nonlinear? Well, we really can't make that determination if we haven't simplified, okay? It already says y equals, but over here, this is not simplified because when we have parentheses, things are not simplified. So we need to simplify this first, and we need to distribute that 4. So when we distribute the 4, we end up with 4x minus 4. And then question, does this look like y equals mx plus b? And I'd say, well, yeah. This has that invisible 1, right, that exponent, so the x looks good. There's an m right here. It's being multiplied, and the x is in the numerator. So then I have minus 4. So if it is a linear function, you should be able to immediately from the equation tell me what the slope is and what the y-intercept is. So this is your proof after simplifying that it is a linear function. Okay, so the question we ask when we get equations, we got to solve for y. Maybe you have to bubble and box. Maybe you have to do some rearranging. You make it look like y equals, and then on this side, once you've simplified it, does it meet the requirements of y equals mx plus b? All right? All right, guys, so last one here. So again, we're asking the question, linear versus nonlinear, but now we're looking at graphs. This is by far the easiest one yet. The question you ask is the graph a straight line? So immediately you should look at this and you should be able to say non-linear because this is not a straight line. And so if you're on a test, if you're on a quiz and it says explain, friends, it just takes a few seconds. You say non-linear because the graph is not a straight line. Okay? Now, let's say that you have a graph that is a straight line, like this. I've had several people ask, does it have to go through the origin? No, it does not. The only qualification is that the line is straight, which means that it has a constant rise over run. Okay? So you could have a negative slope line. You could have a positive slope line. You could have a horizontal line. So when we're asking the question about linear versus nonlinear, all of these straight lines work, and it does not have to go through the origin. Okay? So this is probably the most simplest of them all. Just make sure that you keep straight if you're asking the question about function. If you're asking the question about function, then we're going to make sure that for every input, there's only one output, which means we'll use the vertical line test, okay? To make sure that at any given time, when you do a vertical line, does it only cross once? When you do a vertical line, it only crosses once. When you do a vertical line, it only crosses once. When you're checking for linear, nonlinear, then we're saying simply, is it a straight line? Okay, so it's really easy to confuse that we're answering questions about functions or linear, nonlinear, and kind of blend them together. Remember, they are two separate questions, but when we're asking linear versus nonlinear, It is just simply asking, is it a straight line? Yes or no? So this graph here is nonlinear. All right, guys, I hope that helped. I will see you guys in the next discussion.